This is Mr. Anderson for Kellogg Community College, and we're going to be looking at the first section of Chapter 9, Composite and Inverse Functions. We're going to be also, I strongly recommend a graphing calculator for the end of this section here. We're going to look at some composite functions. The composite function, f of g, is the composition of f and g and is defined as f of g of x. Now, a composition is when you can plug a function into another function. In other words, what you're going to do is you're going to plug the equation of g of x into the equation of f of x. So when we have this composition, we're putting one function inside of another function. Now, what each of these problems is going to do, they're going to have four parts. The first part is you're going to plug g into f if g is 1, plug f into g if f is 1, then plug g into f using the variable x, and then plug f into g using the variable x. So let's take a look at this composition of these functions. I've got x plus 4 and x squared minus 5. Now what I'm going to do is I'm going to plug 1 in for my g. So I'm going to take g of x, which is 1, and I'm going to plug that into the letter x, which is going to be 1 squared minus 5. 1 minus 5 is negative 4. So my g of 1 is equal to negative 4. Now I'm going to plug that into my f of x. So now I have f of negative 4, because I take whatever number I have from that problem and plug it into the x of my f, and now I have negative 4 plus 4, and that gives me an answer of 0. So what I have here is I have f of g of x, which instead of plugging in x, I plugged in 1. So it's f of g of 1 is equal to 0. To review, I plugged 1 into my g and solved for that problem. Just, figured out what it came to, and then plug that into my x of my function f, and that is solving f of g of 1. Now I'm going to do the same thing over here, but instead I'm going to start off with my f, since my f is getting plugged into g, work from inside out. So f of 1 is equal to 1 plus 4. So f of 1 is equal to 5. So 1 when plugged into the function f gave me 5. Now I'm going to take my g and I'm going to plug 5 into it, since we're going to plug the number into g, whatever it came to from the function f. So this is going to give me 5 squared minus 5, or 25 minus 5. So my answer is going to be 20. So what this gives me is it gives me my g of f of 1 is equal to 20. So in review, a composition function is when you plug one function in for the other one. And we do so using whole numbers here, or using integers, or wherever they give you in the problems, is that you have to plug the number in for the one that's starting with the one that's going on the inside. So it's the second one in each of these lists. So plug the 1 into g, then figure out what that is, and then plug it, whatever that number is, into f, and then you've found your f of g of 1. Now I've written it a different way in my answers. You'll notice that these are equivalent. So f of g is the same thing as writing f of g of x. These are the same kind of writings there. Now for C and D, you'll notice that they don't actually have numbers, they just have letters. So what you'll do for C and D is you're going to plug the g into the f equation. So it's kind of nice that I got rid of the things that I actually had on the screen here, because what I'm going to do is I'm going to take my f of x and plug my g into that. So it's going to be, in parentheses, x squared minus 5 plus 4. So this is my f of g of x. So I take my f of x and plug this into it. Now that becomes f of g of x, because I plugged this inside there. So it's x squared minus 1. Now I'm going to do the same thing here. I'm going to start off with my g of x, which is going to be x squared minus 5, but instead of writing x squared, I'm going to take my f and substitute that in for the x squared. So this is x plus 4 minus 5. Now this is g of f of x, because I plugged my f of x into my g. And then this makes, I can just FOIL this out here, this is going to be x squared plus 8x plus 16 minus 5. That's this FOILed. So this makes x squared plus 8x plus 16 minus 5, x squared plus 8x plus 11. And there's my answer there for my g of f of x. So for A and B, you're going to plug in the whole numbers, and for C and D, you're going to plug in the letters, or plug in one equation in for the other. So let's do 2 more of these kinds of problems here. And it's gone off the screen here, but just to remind you, for part A, what I'm going to do is do my f of g. So we're going to find this out for A. This is going to be my f of g of 1. So I'm going to take my 1 and plug it into my g of x there. So this is 1 plus 2. G of 1 is equal to 3. Then I'm going to take that and plug into my f. So now I've got f of 3, which is 1 over 3 squared, which is 1 over 9. So my answer of f of g of 1 is going to be 1/9. Okay, moving on to the next problem here. This is going to be my g of f of 1. So I'm going to take my 1 and plug it in for my f. Plug in 1 in for f. It's going to be pretty good. 1 over 1 squared. So 1 over 1 squared is 1 over 1, which is 1. So my f of 1 is 1. And then I'm going to plug g of 1 into the problem. So g of 1 is equal to 1 plus 2. G of 1 is equal to 3. So now that I'm at my answer here, that means my g of f of 1 is equal to 3. Alright, now what we'll do for letter C is plug one equation in for the other. Now for my f of g of x, I'm going to plug my g into my f equation. So my f equation is 1 over x squared. Well, this would be 1 over x plus 2 quantity squared. And I know the book leaves it in this form, but there's no reason why we can't FOIL this out. X squared plus 4x plus 4. And there it is. There's my f of g of x. Now let's go g of f of x. What this means is I'm going to plug my f of x equation into my g of x. So here's my g of x, x plus 2, but instead of x plus 2, I'm going to write 1 over x squared plus 2. So, and this is my end function. There's nothing to simplify with this anymore. Alright, let's look at problem 3. Alright, let's plug 1 in for my, this is going to be, whoops, hold on, let me click this, click. Alright, here we go. F of g of 1. Now notice I'm writing this a different way. So let's start this out by plugging 1 in for g. So g of 1 is equal to 13 over 1, which is equal to 13. So my g of 1 is equal to 13, which means I plug my 13 in for f, and this gives me the square root of 13 plus 3, which gives me the square root of 16, which is going to give me plus or minus 4, but we're going to just simplify things right now and just leave that as 4, even though when you take the square root you could take plus or minus 4. So just know that in the back of your head. F of g of 1 is equal to 4. Alright, now we're going to do the same thing, except we're going to start off with f of x, because this is going to be g of f of 1. Alright. So let's keep going from here. Let's start off with my f of 1. So here's my f1, and that's the square root of 1 plus 4, which is technically plus or minus 2, but we'll just keep this as 2 here. Then what we'll do is, since that was my f of 1 is equal to 2, let's put my g of 2 into my equation, which is 13 over 2. And there's nothing to simplify there anymore, because 13 halves can't be made any more simple. So what we have here is g of f of 1 is equal to 13 halves, or 6 1/2. 6.5. I mean, any way we want to do it, really. All right, now what we're going to do is we're going to get our, look, I'm just changing the notation just to show you we can. There's my f of g of x. I'm going to plug my g into my f. My f is a square root right there, but I'm going to plug my g of x into it, 13x plus 3, and there it is. My f of g of x is equal to 13x plus 3. Yeah, there could be some extra work here if you wanted to get rid of the denominator in the radical, but then again, we can just keep it like this. The whole purpose is just to know which way things are going into each other. And again, I'm writing it like this, the g of f of x, just to show you that these two are interchangeable the way I'm writing them. You can write them as nested parentheses or in this style. It doesn't really make a difference. So what I start off with my g of x equation, and I'm going to stuff my f of x right into that, which is the square root of x plus 3. You could rationalize a denominator, but that's not going to be the important part of this lesson. So instead of traveling down a 5 to 10 minute route with that, it's just best to just kind of leave it as it is, like your book does. All right, so moving on to page 2. All right, so now there's here's an idea. You kind of have to use your creative skills to figure out how can we get this composite function, because this h of x is a composite function where we plug g into f. So create your own examples. One of the easiest examples is to think, well, maybe f of x started out as like x cubed, and my g of x is 2x plus 7. So you can see how the composite of this, how f of g of x would be plugging this into this, so it would be the cubic root of 2x plus 7. Or the cubic, not a cubic root, the cubic of 2x plus 7. So this right here matches, so I came up with a possibility. Same thing over here. Imagine my f of x was just 3 over x, and then my g of x is x plus 4. So if I plug that into that, my composite of the two, my f of g, again, just showing you that I can write this any way I want to. Their f of g of x is equal to 3 over x plus 4, which is the same thing as that. So therefore, this is one example. Now the answers may vary, so you'll have to kind of think of your own way to make this to work, because other people could have come up with other ways to do this. Okay, now we're going to take just a little bit of a sideline here and to think about this part, which is what does it mean that a function is one-to-one? One-to-one here is if different inputs have different outputs. Now, one-to-one, to test to see if different inputs have different outputs, we have the horizontal line test. Now, if you're remembering these line tests, now way back in the first test that we had a line test to test whether something is a function or not, and that was called the vertical line test. But now we have a horizontal line test, because if we have a function like y equals x squared, it's not one-to-one, because see, this is what it looks like. This fails the horizontal line test because two inputs share the same output. Like this input here and this input here on the x-axis, they share the same output. What's important about these is that if a function is not one-to-one, then it does not have an inverse. Okay, so that's important. So if something fails the horizontal line test, that means no inverse. Or actually, I should say instead of no inverse. Now, of course, I'm writing down no inverse, but that is if it fails the horizontal line test. If it fails the horizontal line test, then there's no inverse to the function. And now you might be thinking, well, why do I even care about inverse functions? What's so important about them? Well, inverse functions are going to be really important because that's the real surefire way to graph a logarithm. And logarithmic graphs are very important to graph and very important to learn. So this whole idea of a graph and its inverse deals with something that we need to know how to process, because your technology, as good as it isn't very good at graphing logarithms, so especially ones that are not base 10. But anyway, let's get back to another example here. Now, you might have noticed that x squared fails the horizontal line test. Well, so would any x to the even power would fail the horizontal line test, which means that odd powers should be safe, but not all of them are safe. Some x to the odd powers, and I should say some of them, not all of them, are not actually safe. For example here, let's say I have x cubed minus 2x minus 5. And if you graph that, it would actually have a bend in it like this, so it fails the horizontal line test because more than one input have the same output, like this input, and this input, all the same output. So these are examples of failing the horizontal line test. So all even powers fail, some odd powers fail. And there's some notes here that I wrote down that you might find interesting, because these notes really get into the nuts and bolts of it and might show up a little bit more later. They might show up more later in the review here. See, if a formula is 1-to-1 and it has an inverse function, okay, so that means if it passes the horizontal line test, it has an inverse. An inverse function is like an, oh, wow. An inverse function is like an inverse operation in the idea that it takes us back to the original value of x. So if I take the function in its inverse, it will take me all the way back to x, and vice versa. You're actually going to see that written out in class a little bit, but I don't really want to spend time on the video here, even though you might be tested on this on the review of your test here. So what I'm going to do is, for these problems, for your next set of work here, you have to determine if the function is 1-to-1. So does it fail the horizontal line test? And what I'm going to use is a calculator here, and I'm going to do this kind of in a different order, because I'll notice that every time I have to do a function, it will erase what I have on the screen here. So what I'm going to do is just kind of do each one of these problems with you on the calculator and show you which ones are 1-to-1 and which ones are not 1-to-1. So let's go turn this on and just go through these 6 problems and see which ones are 1-to-1 or not. So I'm going to type in 3x. It's an odd power, so I'm pretty much, you know, I have to check any odd power to see if it's 1-to-1 or not. And this is definitely 1-to-1 because the horizontal line test passes here. Let's look at the next one. It's another odd power, so I have to check it. Any odd powers need to be checked. Plus 2. All right, and this is another function that's 1-to-1 because the horizontal line test passes in this case, even though it looks like the horizontal line test fails, but this is just because of the pixels on the screen. It doesn't actually go through more than one place at one time. I can tell number 8 definitely is going to pass because this is just 7 minus x. If number 6 passed, number 8 is going to pass pretty much with flying colors. There you go. All right, now this one, this is not an odd power, nor is it an even power. This is a power of 0. This is an x equals, or y equals 8, and well, that gives you a horizontal line. So number 9 is not does not have an inverse, and it does not have an inverse because it would be a vertical line, which is not a function. There's a lot of discussion to be had at that, but this fails the horizontal line test, so it is not 1-to-1. Number 9, nope, not 1-to-1. Okay, number 10 here, we're going to have x cubed. Okay, so this is a cubic, so we have to check it. Minus 4. And there it is. This passes the horizontal line test. It may seem like it fails right there, but this is a continuous curve that moves up the graph. It never stops, so it does not fail the horizontal line test, nor will this one. This one is going to be the square root of x minus 1. This is going to look like this. Does not fail the horizontal line test. Even though it looks like it flattens out, this constantly increases, but it does so at such a slow rate. It doesn't really look like that on the screen. All right, so let's remember those 6 tests here as we go back and, whoops, as we go back and try to center the screen. Sorry about that. And then get to some graphing on the back page. F of x is equal to 3 of x. Okay, so was this 1-to-1? And since it passed the horizontal line test, yes. And I'll just put these down here. Yes, yes, yes. And no. All right, so find a formula for the inverse. Okay, so now what we're going to do is we're going to find f of -1, which is the inverse function. The inverse function is going to be the kind of an opposite of this function. Graphically, it won't. You'll kind of see what that looks like, but to get an inverse of a function, you're going to take your original function, y equals 3x, and then switch places of x and y, and then solve for y. And that's how you find the inverse function. Divide both sides by 3. Y is equal to x over 3. So my inverse function for this function is going to be, hold on, got to put my x in there, is going to be x over 3. So my original function is 3x, my inverse function is x over 3, and if I plugged one into the other, I would get a value of x, because the inverse function of 3 and division of 3 is x. That's where that little this means if you can plug the function into the inverse function or vice versa, you'll get x. That's where this is coming into play. Definitely going to be spending a lot more time on that in class than I will be on this video. Alright, so here's another finding the inverse function where I take my equation y equals 1/3 x plus 2 and switch my x and y like so. Move the 2 to the other side, x minus 2 equals 1/3 y. Clear the 1/3 by multiplying everything by 3. 3x minus 6 equals y. So my inverse function here of x is going to be 3x minus 6. So that's how you find an inverse function. You just take your equation, your y equals 7 minus x, flip your x's and y's, and then move everything over. X minus 7 equals negative y. Divide everything by -1. Negative x plus 7 equals y, which means my f of negative... I used f. I should use h. H. My inverse of h of x is going to be negative x plus 7. Alright, no inverse for something that is not 1-to-1. Alright, 2 more problems here. Problem number 10, 11, and then we'll get to the graphing, the cool reveal at the end. I love the graphing, especially for those of you who have had some good geometry classes in the past. You will see some of this some of this old stuff sneaking in here. Alright, so yeah, we found out that both of these were definitely 1-to-1. So let's go take a look now. We're going to take my y equals x cubed minus 4, flip the x and y, so I've got x is equal to y cubed minus 4, move the 4, x plus 4 equals y cubed, take the cubic root of x plus 4 equals y, x plus 4 equals, oh man, I really messed that up, equals y, and that then translates into f. The inverse of f is equal to the cubic root of x plus 4. Alright, I don't really need a parenthesis there. Sorry about that, these little mistakes. Alright, sorry to make that messy. Okay, so what we're going to do here, take our equation, y equals the square root of x minus 1, x minus 1, and then flip-flop, we got x is equal to the square root of y minus 1. And then just square both sides, so we get x squared is equal to y minus 1. And then move the 1 to the other side, x squared plus 1 equals y. So what that makes is my inverse of f of x is equal to x squared plus 1. Bam. There's my inverse equation. Oh heck, I'm going to do this anyway. If you plug the inverse in for the original equation, you'll get x. I said I wasn't going to do this, but now I'm just so carried away with the problem. So what happens if I plug my into my f of x my inverse equation? What happens then? Alright, so I have my equation here, which is going to be the x minus 1, but now I'm going to plug in instead, I'm going to have my x squared plus 1 minus 1. Alright, and then that gives me the square root of x squared, because then plus 1 and minus 1 go to 0. The square root of x squared is x. So this is the way to check to see if you got these problems right, is you can plug your inverse back into your equation and you'll always get the answer of x for each of these problems. And it works the same thing over here. If I plug this back into this equation, I'd have, like, this is plugging my inverse into my equation here. I would get the cubic root of x plus 4 into the cube minus 4 So if I cube the cube root, I get x plus 4 minus 4, which leaves me with x. Yay! So I got a little bit of chance here to kind of show you what I do in class to prove that the inverse, if plugged back in for the problem itself, would always give you the variable x. Alright, it's time to do some graphing. I love these. Alright, so let's talk about graphing. What do I need when I graph? Well, the thing is when I graph, I need to have probably 5 really good points. So let's first of all graph the original function here. Let's graph 1/4 or 0.25. You can write that as 1/4 if you'd like to, in parentheses 1 divided by 4, x plus 2, and then hit the graph button and see what that looks like, which is pretty cool. Then what I'm going to do is I'm going to probably want you to, since when I click back to the calculator here, all the screen here goes away. Got to be a little crafty with this here. So what I'm going to do here is just go to the table and ask you to plot some pretty points. Now, I like to do 5 pretty points, but if you could do 3 really good ones on the straight lines will be okay. So 4 looks like a pretty good deal there, and so does 0, and so does -4. Those look like pretty easy points to plot, so let's go and do that here. So let me get that up on the screen. Alright, so let's go draw. My points were -4, 1, 0, 2, and 4, 3. Alright, so there's my line, drawing like that. Okay, now what I'm going to do is get my inverse. It says graph each function and its inverse, so we start off with y equals 1/4 x. What I'm going to do is get my inverse equation, and then I'm going to go to my switch my x and y. So this is going to be 1/4 x, or y, excuse me, plus 2. Move the 2 to the other side. X minus 2 equals 1/4 y. Multiply everything by 4. 4x minus 8 equals y. And there's my equation. Now what this is going to give me is going to give me a start at -8 if you're using your slope and y-intercept. And this is going to rise 4 and run 1. 1, 2, 3. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. Alright, and now I'm going to have another line. Now, here's what's cool about this. The graph of the line and the inverse, they make a reflection over this y equals, there's another line that we're not printing on this, but there's a line called y equals x, where y is 0, x is 0, y is 1, x is 1, y is 2, x is 2. So this blue dotted line, light blue dotted line, this inverse that I've made, the first line, which is my g of x, and this is my, here, let me put that back in the colors that I was using. Alright, so this is my original g of x here. Here's my g of x, and here's my inverse of the inverse of g of x, and you can see that it's a reflection over this blue y equals x line, and that's where maybe some of your geometry come at you. Now let me go back to the calculators and show you on the screen here, since this is going to go away unfortunately. If I go type in that second equation, which is 4x minus 8, there you go, there's the second line that we drew. And if I draw a third line, which is my y equals x, there's the line they reflect over right there. So you can see that there's always going to be this cool reflection of a line and its inverse, and we'll take a look at that more with exponential lines and the logarithms of those exponential lines. Alright, now we got one more problem to go here, so let's go scroll on down. Now what's funny about this problem here is that this problem, it fails the vertical line test if you actually drew it out as a x squared graph, but this is the square root of x, which only has half of it drawn. There's actually no other half to the line drawn. You can see that I still have this line that's going diagonally. This is where it's going to get reflected over. And first of all, you're probably going to want to plot some pretty points. 0s definitely are pretty points, as there are the domain of this is 0 or greater. The x values have to be greater than or equal to 0. 1, 1 is a pretty point, and 4, 2 is a pretty point. So let's get that graph up here And oops, let's get back here, scroll the screen just a little bit. Okay, now I will rewrite the problem here so you can see it. There we go. So what I have here is, again, the equation is y equals the square root of x, which is 0, 0, 1, 1, and then at 4 it's 2. That means 9 would be 3. And there you go, there's your curve. Now what we're going to do is to get that was my f of x right there. So my f of x is equal to square root of x. So my inverse of f of x is going to be taking my y and my x and flip-flopping their positions. So I've got x is equal to the square root of y. Square both sides, x squared is equal to y, but there's a little thing about x squared being is equal to y. See, my domain is going to be x greater than or equal to 0. I'm not going to basically make the smile that x squared would make for my graph here because of my domain restriction of the first problem. In my first problem, x had to be greater than or equal to 0, so my second problem, that same thing applies. So in this case, since I want to use a different color here so you can kind of track on what I'm doing, let me change the color to red. X squared is going to be this on the table. If you look at this on your calculator, you'll have a 0, 0, so I'll put a red dot right there. 1 will also be 1, so here's that right there. But 2 will be 4 and 3 will be 9. So in this case, you can see that this is going to be an inverse of the other graph going through that light blue line. Remember the light blue line that we talked about? You can still see it on the screen over here on the calculator. But in that light blue line that's going like this, you see that there is symmetry between the two lines. And unfortunately, when I draw this on the calculator, it would make a complete smile, like it would make the smile that goes like this. And because there's no we can't tell the calculator, hey, you can't use this part of the line right there. You can't use that. So getting this on the screen of the calculator is actually not accurate, whereas getting this on your worksheet is accurate because of the restriction on the domain. And this has been this comes to the end of our first section here. Thank you for watching. Again, if you have any questions, just talk to me in class or email me. Thank you.